Starting from 20 minutes working, part presentation will be 10 minutes. And then after comment, you may submit the by midnight today or 18. And here and myself, three of us will start reading. Another change of schedule is has not changed this schedule so that next week we will have this special lecture on Tuesday, and the other schedule are delayed. And Professor Park's schedule is still same. Any question? No? Yeah, let's start. This is my thesis.
So today I will be presenting our midterm presentation, drone-based marine structure inspection system. Before we dive into our today's presentation, let's take a moment to review our what we discussed in the previous presentation. As you may recall, Korea has experienced numerous historical earthquakes, which has led to increasing emphasis on regular safety inspection and maintenance of structures. However, the current inspection system presents several challenges such as labor and safety risks, accessibility issues, accuracy concerns, and also the difficulty of conducting regular inspections. To address these challenges, our team proposed a drone-based inspection system which utilizes some sensors, and we also introduced some potential sensors for inspection in the last presentation, but have not yet decided which ones to use. So therefore, today in this presentation, we will be finalizing the specific sensors for the inspection. The main goal of our project is to develop a method to use drones for inspecting marine structures for defects, ring operation. And as you can see in the left side of the slide, you can see a summary of what we covered in the last presentation. While the right side, there are some comments and feedbacks we received from the professor. So based on that, we refine our project, and improve our presentation material. And this slide shows our project timeline. And today we will focus on these three key points. The first one is first I will decide which structure to instance. Next, I will determine what kind of defects we will be inspecting. And lastly, I will select the sensors that will be used for the inspection. So we have the clear roadmap. So let's get started. Last presentation, we introduced two types of marine structures. First one is floating marine structure, and second one is fixed marine structure. The first floating marine structure are designed to remain stable regardless of the weather or water depth, and also it includes ships. And the fixed marine structures are designed to be fixed on the stable to withstand its own weight and environmental loss. And after discussing with our team, we decided to inspect the fixed marine structure for inspection. And specifically, we chose to inspect the offshore oil platform. These platforms are used for drilling and extracting the oil and natural gases, and is usually located in deep waters where they are exposed to extreme environmental conditions. As a result, they can deteriorate rapidly. And another problem of the offshore oil platform inspection is that the traditional inspection methods in such extreme environmental conditions pose significant risks to the human inspector, and it is also time consuming. So to solve these problems, our team proposed the drone-based inspection. By using drone, we can cover the large areas more efficiently and safely. And also, plus we can obtain some data, which is hard to reach areas. On this slide, you can see examples of inspection points with drones. These areas can be monitored. So now we determine structure to inspect. The next step is we need to determine which defects we will detect. Our team identified the four major defects. The first one is corrosion. Corrosion can occur due to the exposure to seawater, and it sometimes can be visible to the naked eye. Also, it can be occur in the inside of the structure. And since it weakens the structure over time, so it is important to detect the corrosion early. The next one is that cracks can occur due to the constant stress exerted by ocean waves, and also appear either inside and outside of the structure. And even small cracks are dangerous because they can get quickly and lead to the serious damage. Next one is fatigue. But similar to cracks, fatigue can occur due to the continuous stress and also the heavy weight. The scary thing, one of the scary thing of the fatigue is it often goes unnoticed, but the failure can be occur suddenly. So it's important to the regular inspection is important to the fatigue. And last one is structure deformation. Structure can become deformed due to the pressure exerted by ocean wave and also weight of heavy machinery. The deformation can accelerate the fatigue, so it is also important to detect the structure, especially the areas expected to bear heavy. So to detect these defects, we need some sensors in our team. select these two sensors. The first one is high resolution camera. This will allow us to detect the surface defects in real time, and it is also useful for covering large sections. And for example, with the high resolution camera, we can detect surface rust, surface cracks, and other if defects cannot be easily classified in the naked eye, we will use a convolutional neural network, as known as CNN. CNN is one of the type of artificial neural network which help us to classify the defects more easily. The next one is thermal image sensor. This will allow us to detect the hidden defects and hit anomaly, making it useful for inspecting internal issues. With thermal image sensor, we can detect the internal corrosion, internal cracks, and pipeline leakage that are otherwise invisible to the naked eye. So by using the drone, we can expect some kind of key advantages. The first one is reduced human risk. Drone take on difficult and dangerous tasks, which mean fewer safety accidents and much better profession for workers. The next one is the ability to assess hard to reach area. Drone enable remote remote monitoring, so we can collect the data from places that can be difficult or dangerous for human inspector, regardless of the weather. And next one is the enhanced effect detection. With high resolution camera, we can collect or capture the detailed data, and we can identify the defects with greater precision. And lastly, the drones allow for more frequent inspection. By increasing the frequency of inspection, we can improve our chances of detecting the defects early before they become serious damage. So in conclusion, today I focused on these three key points. When I decided with the offshore oil platform to inspect, and I identified the four major defects: pollution, cracks, leaks, and structure deformation. And lastly, I select the high resolution camera and thermal image sensor for the inspection. And next presentation, we will discuss the treatment of our presentation. This slide shows the job allocation within our team. And since it is the same as the last presentation, so I will skip over it. This is a reference that our team used for project. Thank you for your attention. And if you have any questions, feel free to ask. And two questions. First one is, it is possible to sufficiently ensure the scalability of the drones in bad environments, such as when it's raining or the wind is strong, and especially the our main goal was to develop a method to use drones. So that is kind of the modeling of the drone. That is the modeling of the drone. So if our team change final goals quickly, decided that I have a problem or so, but I didn't think we didn't think about that kind of drone, so next time we will think about that and tell.
Another question is while the drone is flying, there will be a lot of vibration of itself. It is possible to quantify the vibration so level well detect or information can be meaningful.
That question. Also, I think that so things prior to so, um, we didn't think about the controlling the drones or designing the drones. So because of the initial to use drone for inspection, so it often will discuss with our teammates and their team.
Are you going to use the cameras in the flying with the flying drone or drone in the stable? You position the drone in the stable position and then use the camera.
Uh, we will attach the what it mean sensors outside or outside. Uh, I think the it will capture while it is flying. So I I also think it is really important to control the drone's posture. So we that's not really because
Any other question from other team members? No. TA. No question? I see there has been a good progress, but still you need more details. Something like a location of the structure. Depending on the location, the requirement can be different. Also, where is the location of the operator of the drone?
usually in the street, not too far from the platform.
Also, it is depending on the patient. The operator may stay on board the offshore structure. Think about it. But depending on the situation and location and other items. So finally, I propose you need to separate our minimum goal and maximum goal. You did not show us the minimum, which must be finished by end of the semester. Please provide it. All right, thank you very much. We can move on to team four. 파일 좀 닫아줄래?
My name is Song and we are team four, so I will do this on a report. Before we start, our subject was the general design and the feasibility check of the server data center. So we present that much about our subject. And today we will focus on the detail about our course. So we had three objectives right here, and our design, we are gonna design a system that is able to transfer the data within the network, and it is able to take away the hits from the device with, or maybe we can, if can, without the energy, and also should be no side effects. So, based on this objective, we set some considerations right there. So there are four considerations. So we are gonna do these considerations during midterm and final project. So there are some requirements right here and structural boards like a general arrangement and is it the hydrostatic pressure. And the hidden energy is the most important consideration. So the estimation of the total heat emission and how we're gonna design a coolant channel or the coolant system. And lastly, if we can, we are gonna search for some environmental effect. So the first one is some basic research of the data center, like market size and the energy usage and the location of data center in Korea. So in the market side, we are gonna there keep rising in the usage of the data center, and because of that, the amount of the energy the consumed for the data center is also rising, and we're gonna rising consistently. And the third picture is the location of the data center on the ground in the Korea. So basically, in more than the half of the data center is built in Seoul, Gyeonggi, Incheon. And as you know, the half of the citizen is people is living in Seoul, Gyeonggi, Incheon. And Busan and Gangwon was the second and third in our country. So it is okay. And the next one is so I'll show you some case of the data center. So on the left side is a data center from the neighbor, and the right side is located in Ansan. It's a Kakao IDC. So for the neighbor data center, they have 600,000 units, and for the Kakao, they have 4,000 racks. And usually, they may depend on some size. One rack equals to 42 unit, and the unit is the if you have seen some movies or like Hollywood movie, you may have shown a server room, and one basic unit of for in the server is called the unit in here. So one rack is the total power and the bundle of the unit. There are many server units in the data center, and for the entire global energy consumption, about 1.4% of the energy is used for data center. And in the data center, about 43% of the entire energy usage is for the cooling system. So based on this research, we detailed our design targets. So in our project, we're gonna design a data center with 10,000 racks, and these data devices will be modularized in some cubic shape, and should be easy to install and easy to maintenance. And in the energy board, we're gonna shrink the energy consumption for 50%, and it the data center will be able to submerge under the 100 meter of the sea level. So we're gonna determine where the location should be and how much space is needed and the amount of the heat radiation, the estimation of the heat radiation, and how we're gonna construct these devices and how the cooling system mechanism will work. So for the consideration of the location, we excluded the Namhae South Sea because it's far from the Gyeonggi, and so we're gonna compare the Yellow Sea near the Incheon and the East Sea near the Gangneung. So for the salinity around our sea, so there should be more salt in the East Sea, because in the Yellow Sea, the West Sea, there are many rivers, including ours and China and some North Korea something. So the salt is much higher in the East Sea, and for the deepness, the East Sea is much deeper than the Yellow Sea. And for the temperature, also the cold current is passing through in the East Sea, so the temperature is much lower than the Yellow Sea. So so this is the main reason why we choose to construct this data center in the East Sea. In the Yellow Sea, the West Sea, there is a dead burn, so it's hard to construct for something in under the water. So in our consideration, East Sea is a better option. That was the location selection, and the next one is how much speed will be needed and how much the amount of the heat radiation, the estimation of the heat radiation. So we're gonna modularize this server in some container-shaped chamber. I'm not saying that we're gonna use the container-shaped chamber. So if we model this server rack, model of the rack, it will be easy to model and its operation easy to make and modify. So about in the size of the container, about 20 racks can be contained. So if we are target to build 10,000 rack data center, we're gonna need about 500 or 600 module is needed. So in every each module, the container size, the one data module use 300 kilowatt energy. So in the cooling system, we're gonna need about 130 kilowatts. And the next one for the construction method, there's a many construction methods in the underwater system, and we choose to construct in the monopile system. So this is the basic concept design of our data center. So there is a modularized data center, the blue one, and around the data center there will be some monopile, copper monopile right there, and they acts like a pillar of the structure. And there is a lifting devices right there in the monopile. So these devices can make the data center go up and down in the underwater. So that will be very help to maintain the data center. And also, and since this is a monopile structure, there may have some another wind turbine system to manage the electricity under the water. And the last one is the cooling system mechanism. So inside the data center module, there will be some coolant channel right there, and the heat pipe will convey the heat from the generated from the server into the coolant water. So, and another thing is that if the temperature gradient is occurred, there may be some acceleration for the natural convection like here. So, without using some fan, there may be some natural flow can be occurred in the coolant channel. So maybe we can use this kind of flow. So this is the conclusion for the midterm presentation. The selection of the location, the East Sea is suitable, more suitable than the Yellow Sea. And for the structure, one container, one chamber can handle about 20 racks, and it will need about 500 or 600 chambers. And there should be a multiple monopile structure and water lifting devices management. And for the cooling system, natural convection flow system due to temperature stresses can be used, and racks are surrounded by mineral oil, so they can diffuse the heat faster. And in the final presentation, we're gonna do some verification of the structure and cooling system design, and we're gonna inspect the influence of the near ocean in the aspect of the system. Well, this is my presentation.
person is that if the monofilament system have any advantages in terms of repair and maintenance of the device. In the second one, did you found approximate cost of building and maintenance or maintaining the
So we compare the other structure like a jacket or the supporting devices, and the monoplier is much cheaper than the other, than the jacket design. And for the floating devices, we have considered some floating devices, but in the structural stability, we we decided that not the floating, the 고정형 devices is much more suitable than the other floating devices. So we choose to modify and model.
building maintenance?
Ah, I show them to the final. We did not introduce that. 아직 미완이에요.
Other question? No? TA? No question? All right. Simple question is, you may better to show us the size of the rack. Do you know the size? Typical rack?
They usually 600 millimeter, 600 millimeter,
2 meter?
네, 이건 규격화가 돼 있어요.
Please write down.
네.
And then what can be the water depth you need to locate? It is submerged, right?
Yes. We suspect on less than 100.
And you choose to locate in East Sea, then the cable to connect from the server to the company or the users can be very long, but the cost can be very high. That's why the other companies choose the location in Ansan, even though the land cost is very high comparing to Gangwon-do or something, right? So you need to also consider about the cable cost because it is very high because the data flow requirement is very high, right? Giga or higher than giga. Then the cost is much bigger than thin cable. Thick cable or large cable, the cabling cost is very high. And we need to consider as the other question, the economy. Finally, you may need to have a comparison table with another competing proposals coming from Microsoft and or even Team 6 is doing similar work, right? I heard there is another company, international company, Microsoft and China, something from previous presentation. So you may have a comparison table, then you can find a better way to go. Also, the minimum goal should be. Thank you very much. June 5.
Excellent. Presenter of the team five for the power presentation. Today I'll explain our topic, the effective underwater film analysis using AI trained data and CFD. Underwater exploration is a field with various potential. However, it has a significant limitations due to its extreme environmental conditions such as fast currents, high pressure. To apply engineering systems to these kind of harsh conditions, we have to consider a high level of uncertainty. For the future constructions, stability and assessment often require evaluation using CFD simulation. And in addition, analyzing near seabed condition can provide us critical insights into environmental factors. More specifically, seabed topography directly influences the design and installation of offshore structures, and it can also contribute to environmental management by predicting impacts and analyzing expected sediment transport pathways. Various studies in this area have relied on the sonar-based mapping, which is a widely used technique. Recently, however, there has been a growing interest in deep learning methods that is analyze terrain shapes in real time, 3D models, and evaluate them effectively. Despite these advancements, sonar-based methods suffer from the lack of resolution, require extensive post-processing and high cost. On the other hand, deep learning methods also require a large amount of data sets, which can be a significant limitation. Given these defects, we explored this alternative method for that estimation. Among sonar-based data and RGB camera and LiDAR system, we selected RGB image data for estimation because of their cost effectiveness and high resolution, and also the main goal of our project is to develop a robust workflow combining AI and CFD simulations for the underwater terrain analysis, and also using the cost-effective methods compared to prior studies. We also set additional goals to explore the full potential of this workflow, and we're going to solve this for the challenging problem as far as time and resources allow. Our project plan, which we presented earlier, is structured into several stages, and currently we are in the third stage for the implementation. We will now explain the methodology in detail. To perform test estimation, we trained an AI model using RGB image data, and by employing the fine-tuning approach, we can minimize the need for a large data set while achieving a model capable of accurate prediction. And also we use data augmentation for the enhanced robustness of our model, such as image rotation, scaling, and cropping. And our base model was anything big 2 with pre-trained ET data. The training process consists of these 3 main steps: the data generation and labeling, training. As a result, our trained model demonstrated a highly accurate estimation, as you can see in this picture, even within our limited data set. To integrate this data into safety simulations, we performed several post-processing steps. We selected main pairing structure, excluding other elements, and then we created the clean 3D model. Using anti-space clean software, we defined the domain as enclosure to perform external flow simulation. And these are the specific boundary conditions for we implemented in this project, and this is based on the insights this referenced research paper. And as you can see, we set a pre-slip condition on the top side of this external cube, and either left and right side and bottom side. Also, the terrain structure is applied no slip condition because it's just a wall, and we assign inlet as a prescribed velocity boundary condition, and outlet is a pressure boundary condition. More detailed information you can see in this table. For the mesh construction, we generated tetrahedral elements. Number of elements was about 1 million, and we also set insulation from the wall surfaces to mimic the physics of no slip condition. Finally, we calculate the CFD simulation using OpenFOAM, which is well-known open source software. We conduct steady simulation. Gravity was applied. So the solver was we want simple foam, which is one of the solver from the form, and the compilation was terminated when simulation results is fully converged. As a result, we obtained this kind of clean contour of velocity and pressure. And this is just a formation of streamlines and velocity vectors. And for the analysis, we select the points with relevant to velocity and pressure, and we can expect the erosion or structure damage risk would be high on that region. For facial risks, we're going to apply the same methods to several cases, verify that our method can be applied generally, and we have to apply more realistic boundary conditions because the underwater current is not just a steady velocity. We have to think as periodic inlet velocity condition. And then we are going to consider the methods to further develop additional goals to optimize the process of converting the data to CFD applicable formats, and using other numerical methods such as force calculation at this time. Thank you for listening.
So I found is that,
Louder, please.
as I understand, is that your team used RGB camera rather than using sonar and radar system. So this the measurement device need to be some immersed in the sea to use RGB camera. And the second question, can we assume that the influence of wind is ignored in safety?
Thank you for questions. Next question. Yes, the RGB camera have to go dive into the other one. We have to take some submerged. For the second question, we have to be considered for a realistic condition. So we are going to set boundary condition as periodic unit boundary condition, and we are going to search more details that wind or other trends kind of that will be considered in next presentation.
One when the device is submerged in the deeper ocean, light the light intensity will be 500. I think maybe
For that question, there are we are just simply we can just simply use some lights with the RGB camera, and the data we used in this presentation, like as you can see, there are also in the seabed very lower strength. Yes, that so.
Other questions? Yay. Right. You need to also decide on the location. Yes. Because depending on the location, the requirement can be different. As previous question, if you try to use in Yellow Sea, the water is very muddy, so that you cannot catch clear camera photos image. Okay. Or during the night, if the application requires operation during night, you cannot use camera, you need to have a light. So it is depending on the application where you are trying to use this technology and where the location. Depending on the location and applications, the requirement is different. Right? So you need to think about this one. So something like a high resolution is required, then you need to have a clear water or light, right, right, to get a high resolution picture. So depending on the application. And I still cannot get clear picture why you use a CFD simulation in comparing or combined together with the RGB camera. Because my question is, RGB camera gives you the current situation, but CFD simulation gives you a prediction of future. So current situation can be captured by camera. Why you're using CFD? For prediction for terrain change in the future? It's still not clear for me. What is your proposal of using CFD? So it's also depending on the application of your technology.
We'll specify for the third presentation.
Thank you very much. Okay, we can move on to. We have enough time.
The next is the narrative that makes sense. So to review the project proposal. So we talked about data center, how it is to put the data center into the deep sea water. Because one of the biggest problem is the cooling system on data center. And we had a few priorities which were to optimize the way to integrate the data centers with renewable energy and also minimizing the effect on the environment and marine life. So for the content, we'll talk about the system configuration. Then we will summarize all the needs in energy and all the production that we can have for our system, and also all the problems linked to the maintenance of the system. So the basic a wind farm, wind turbine farm offshore. I will give power to the data center, but problem with wind turbine is that the energy supply is not constant. So for this, we need to have a storage that will be done with the liquid hydrogen. Also, the liquid hydrogen will be used as a current the our data center. So we chose to talk about Saint-Nazaire wind farm located in France in the Atlantic Ocean. So the Saint-Nazaire wind farm lies 150 and 60 megawatt turbine, each with a capacity of 6 megawatts totaling and installed capacity of 480 megawatts. So daily energy, we can compare two phases, one with low energy supply and one with more high energy supply, depending on the wind velocity. So for the low energy supplies, we will have 576 megawatt, and for the high energy, it will be 4,320 megawatts. So around 4,896 megawatts per day. So for data center, there's different size with different consumption needs. That was the most ones. So according to that, we'll have needs of 3,120 megawatt a day in total, but with a constant supply for data center. This was used with one of the data centers located in France, so we stay in the same area. So with this, we'll also have a surplus of energy that can be used for, that will still be used in normal consumption from wind farm for this use that. So for the intermittency of the energy supply, we'll use we'll integrate an hydrogen-based energy storage and supply. So the different components will be an electrolyzer, a liquefaction system, storage tank, and the fuel cell. So there's different needs for the electrolyzer. We can spread it into groups, the electrolyzer, the one that will be mostly used to keep the energy and for the battery system. So I won't explain all the number right now. And then the liquefaction process. What we can see is that the liquefaction process used for cooling is required way less energy than for the battery system. And considering this, we will need an refrigerant that will be able to produce an hydrogen mass 1,776 megawatts per day of the hydrogen capacity. So in the end, we have the requirements, the energy requirement that is 780 megawatt. The for low wind energy will have only 576 megawatt produced. So during 6 hours a day, we will be in low energy efficiency. So we need to have a backup of energy of 204 megawatt for those 3 hours. And counting the efficiency of the hydrogen production cells, we will require daily a production of 10 kilograms of hydrogen, 10,000 kilograms of hydrogen. So this is the details about the hydrogen store, because when we will get the hydrogen in tank for the storage and to make new for battery, the problem is that the hydrogen will usually boil off in gas cans. We need to cool it down again. So it will be an additional energy that we need to add in the system. Yeah, constant. So other surplus of hydrogen. So either we can keep some hydrogen in tanks, boiling tanks, but as we know, there's a lot of boiling problems that will require a lot of energy all the time. So, and we don't need to have an infinite energy supply in the data center all the time. So we will have a surplus of energy that we can sell or put back again in the normal, usual system that existed before data center. So now one of the biggest problems also maintenance, because we're underwater. So there's a lot of problems with it. So in our case, we are located in France, and there's 2 categories of offshore wind turbines. The fixed wind turbines that are usually located under 50 meters of depth, and the floating ones that are in a deeper water level, so between 50 and 100 meters. In France, for the moment, the two ones we talked about in the first presentation are all fixed wind turbine under 50 meters. So even if we put the data center in the floor, in the seabed, in the sea, we won't have, it won't exceed 50 meters there. So might be important for sending divers for maintenance. But there's a potential, the most potential in the entire world will be those wind turbines or further away from the coastline. And so we might also need to think about what will happen in this space and how we can put data for this capabilities. So we studied a few existing systems for maintenance. So there's a lot of commercial offshore diving for offshore structures, even wind turbines already that are used to working underwater. And for some of the works, you need to stay underwater for a few weeks, 3 weeks, in very high pressure. And because of that, you cannot go at the surface on top of this every day. It will be really bad for all the divers. So so we went deeper into the saturation diving that where the divers go in underwater habitats in between operations. So they stay for 3 weeks or 4 weeks underwater the whole time. And with it, there's a few underwater habitat. So in a case that we are lucky, the offshore wind farm are pretty with a low depth. We would have an habitat accessible via outside of the water for the entire data center. So problem solved for most of the things. But what we usually have is habitat accessible only by diving, where the energy and breathing supply are and breathing gas are supplied by umbilical cable. So here you have example. This one is a closed diving bell, and it's actually used in by technique in Norway for offshore maintenance. So this is still a project roadmap. We set a maximum goal of visualizing the entire system, and then for minimum goal is to optimize the climate target system and the capital feasibility for real life usage.
Question.
Did you found the cost of construction for maintenance system compared to traditional things?
For the cost for the maintenance part, not now. It's one of the things we're working on. For the general cost.
The roadmap.
Yeah.
Actual feasibility check for real life use for this.
Also the cost check, see if it's something we can, that will be worth doing on. It will be in the capital feasibility. For the maintenance part is, I think, will be the biggest issue for economical.
Is with the underwater like habitat and things like that, right? Is there going to be like have you like considered like the pressure involved that is gonna be on that area?
Yes, that's why for this whole route, it's what we will use, but it will have the entire data center that needs to be accessible. So, but the closed bell actually exists, and they keep a pressure that is the closest to the one that I rely in all day, but it's still 5 volt. So it's kind of a pressure in which they said they talk the high pitched voice, and that's why they don't go back to the surface. And but it's still very complicated working conditions for them. But it's what actually exists right now.
Concerning the location data center, I want to know data transmission distance.
For the moment, I don't have the exact number, but the wind farm are really close to the coastline, because they also need to supply. Actually, they used to supply energy to the coast area, so they shouldn't be like all of the cable and all of the system is already existing. What's this also? Very good.
Discussions. TA. You should have a test. How can you grade it? Right, my one. It's good to see progress. I worry about you have a too much, you broaden up your topics. See, you started from data center, but now today I heard about hydrogen production, that is energy storage. And also you talk about habitat. So already it looks like 3 topics rather than 1 topic. So this is a midterm presentation. You need to narrow down your scope in this channel, but still you are wide enough. So I worry about how can you finish up your project. So once again, you need to have a minimum goal. 2, must finish your minimum goal, right? Because now you have a more subject. Right. About the cost economy, as he said, and also previous team 4, the transmission cost of data can be higher than transmission cost of energy. Offshore energy island or offshore wind farm, they have a problem of transferring energy to the land side because the cost is high. That's why they are thinking about producing hydrogen rather than make a cable. Because they made a comparison between making hydrogen, it also costs, right? And transportation to the land. It is another cost, but sometimes it is better to produce hydrogen rather than have a cable to the land, because cable cost is higher. But I guess transmission cost for data may be much higher than energy cable cost. Then you need to locate a data center near the city. If the data transmission cost is very high, right? So you need to make economic analysis. So that is please write down your minimum goal and try to narrow down. It's good to study. more ideas, good to interesting, very interesting, but I'm worried about you. You cannot finish yours. All right, thank you very much. One idea to hint to the energy storage team. Previous presentation, I raised a question that why the previous existing teams use a water depth of 35 meters. That was my question, right? You didn't answer to this. But my answer to them is they try to make a minimum depth, required minimum depth. Why 35 meters? My guess is the fluctuation of wave do not reach it down to 35 meters. Big wave. Usually half of the length of the wave does not come to the disturb the depth of half of the wavelength. So I guess the near depending on the situation or location, 35 meters is good enough to neglect the wave effect down to 35. That is my assumption or guess. The other one is temperature difference from the surface to the down. It goes down, down, down as deeper, right? There is a curve you can find temperature variation in ocean, depending on the depth. I guess 35 meters is enough to get cool water there and stable temperature. Fluctuation in the surface is higher on temperature-wise because of sunshine and also tide and current. But 35 meters is relatively stable there. So my guess is they choose 35 meters as the minimum depth to be stable patient there. Okay. All right, see you.